Hello everybody, welcome to Unit 4, Lesson 2. In this lesson we're going to learn about structs. Specifically, we're going to go over how to use structs to manipulate data, how to use structs with functions, and how to process an array of structs. And of course, those are your learning objectives as well. In C and C++, structs allow us to define new data types that can hold multiple items of different types. Here's the definition of one struct named houseType. Pay attention to the semicolon at the end of the definition. This syntax is important. Now we can use this data type to create variables. A variable of this type would contain members of the specified types, each occupying space in memory. This is very similar to how a class can have attributes of different types. With this declaration, each data member of this struct will be allocated memory automatically, but the memory locations will be uninitialized. If you peek into the struct variable for this example under the debugging mode of Visual Studio, you can see that each data member holds some junk value. To access the data member, whether it's to get the value or set the value, you use the dot operator with the struct variable, just like you would a class in Java. Here you can see we are setting the style and the number of bathrooms variable. Additionally, the C++ 2011 standard allows an array style list initializer for the struct. This is what the struct holds after this declaration. Be aware that this initializer only provides values for the first 6 data members. The remaining 2 data members will be initialized to 0 of their types. This is the same way a partial initialization works with a statically allocated array. You can directly assign one struct variable to another, like this. It will perform a member-by-member assignment. Now, the struct house2 will hold the same values as struct house1 holds. This is an easy way to copy the contents of one struct to another. All other operations on the struct, such as input, output, and comparison, will need to be done on a member-by-member basis. Table 9-1 in the course textbook lists some ways that a struct compares to an array. And one thing that you might want to pay attention to is the fact that you can actually return a struct from a function right here. So that's extremely useful if you need to bundle up a bunch of different data types instead of having a bunch of reference variables in your function. You can just have it return a struct that has all those particular data types packaged up in that struct. As I previously mentioned, a struct is similar to a class, but how do they differ? And why would we need to use classes if we have structs? Well, to begin with, in a struct, all members are public by default. And that's why we can access individual members using the dot operator like you see here. In contrast, all members of a class are private by default. Therefore, we need to define public member functions for a class in order to access its data members. Don't worry about the syntax specifics right now, we'll get into those later, but for now, it's enough to say that the concept of a class in C++ is the same as it is in Java. I'd also like to point out the difference between C-style structs and C++-style structs. What we see in this chapter is the C-style struct, which only has data members. C++ extends the C struct to allow member functions in a struct. In that way, C++ struct is very close to a class, except for that the members of the struct are public by default. Here you can see our member function that's part of the struct. Real-world C++ projects, however, generally use C-style structs rather than C++-style structs. So we're going to stick to this one right here for the course of this lesson and for the course, but just be aware that you may see this out in the wild. A struct variable can be passed into a function by value or by reference. So here you can see that we are passing it into the house as a the function as a value, and here you can see that we are passing it as a reference. Another thing is that a function can also return a value of a type struct. So here you can see we have this function, add room by value, we're passing in the house, right? And then we're going to return the house that we passed in. And so, so again, it's much like regular variables. You can pass it in by value, by a reference, and you can also return it. So let's take a moment to look at this struct in actual code. So I showed you some function examples, so let's take a look at the whole program. Here you can see we have the struct declaration, right, where we're telling this is what the data structure will look like. We've got the name and we've got all the member variables, right? And then we've got the functions that I just described already. So we've got add room where we're passing it in by value and we're returning an integer of the result. Here we have where we're passing in by a reference where we're not returning anything because it's going to be retained in the reference. And here you can see that we are returning the house type via the function. Okay. In our main program, you can see that I've initialized our struct using the list initializer, and then I'm going to go ahead and add a room. First, I use the pass by value function. So we are going to print out what we currently have in the house, and then we call the add room, and we're displaying the result of that function because remember we're returning it as an integer. And then we're showing you the result of house 1 after we called number of bed, or after we call add room. So you can see up here we're incrementing the size of the number of bedrooms in the house, but you're going to see that if we actually run the code, this is what it's going to look like. Okay, so you can see here that we currently have 3, right? You can see we have 3 right here. Then after our results, we have 4, but then after we print out the result, we still have 3 left in our number of bedrooms. That's because when we passed in our struct as a value, we didn't change the original struct. We didn't change house 1. We changed house, which is a copy of house 1. Okay? So now if we look at it by reference, when we print out the results, okay, we can see that we're currently at 3. And then I call add room by value, okay, and we print out the result, dot number of bedrooms, and then afterwards you can see that our result is 3 as well. And that's because when we print the result, we're calling add room by value, but we're calling the function that returns a house type struct. So then we're calling the number of bedrooms on the house that we returned. Well, again, house here is going to be copied, and we increment the number of bedrooms, and then we return that new data structure. Okay, so when we add rooms, when we print out the results here, house 1 again still hasn't changed. All we've done is changed a copy of it. Finally, in add rooms by reference, here you can see that house 1 currently has 3 bedrooms because it hasn't changed, and we call add rooms by reference. Okay, so right here is that function, and you can see that we're not returning anything, and house.number of bedrooms, we're incrementing it. Now at this point, house is an alias to house 1. So when we add a bedroom, we are actually adding it to the original house 1. So you can see we're printing out the results here where we are actually printing number of bedrooms, and of course afterwards it's going to be the same result. So we have 4 bedrooms now in house 1 instead of just 3. So I wanted to just walk through this to kind of as a refresher and just to get you to think about passing things by reference versus passing things by value and how it changes, because this is a common problem. People will pass an object into a function not realizing that they're passing it by value, and they're going to create a copy of it, and they're not changing the actual result of what they're copying. So I wanted to walk through these 3 examples with this particular struct just to demonstrate that. We can also create an array of structs. Each element of such an array would be a struct variable, which in turn holds multiple members of the struct, as we saw in the previous demo. This illustration here shows how this would be stored in memory. You can see here that we've got this struct of employees, and those employees are going to be stored in an array, and each of those structs has memory space for all of its member variables. So let's go ahead and take a look at this struct in memory. So I created a quick little program to read in some houses from a text file, and so here is our struct. And I took out one of the values just to make looking at it in memory a little bit easier. We'll look at that in a second. But here is the text file where we have a bunch of different house types, you know, apartments and duplexes and whatever, and the size of them, the number of bathrooms, the year they're built, the square footage, the cost and taxes, so on and so forth, right? And you can see those corresponding variables right there. Then, if we take a look, we are going to attempt to open the file. We created some temporary variables, and then we're going to output the size of our data types. So if we take a look at that right here, you'll see that we have a size of 4 for integers, a size of 8 for doubles, right, and a size of 24 for strings. Again, and those are in bytes. Okay, and we use the size of operator to do that. Then I read in all of the files, and then I output the memory location of the first two. And then we set a breakpoint right here to pause the program. So if we take a look at that, all right, and we come to here, we copy this in, and we go to that address, which I was already at, the first 4 bytes is going to be that first integer, the number of bedrooms. And you can see that it's set to equal to 3. Now remember, we're using little endian, so we put our bigger numbers, or we use big endian, excuse me, so our big numbers go in first and our little numbers go in last. So we've got 00000003, which corresponds to the integer 3. Likewise, here's our second integer, 2, right? Here's our next integer right there is C5070000, which corresponds to our space right there, or excuse me, our year that I was built. So if you don't believe me, let's go ahead and pull up a calculator. So we're going to type these in reverse order since we have big ends. So we've got 07C5. So I typed that in hexadecimal, and you can see in decimal it's 1989, which corresponds to the year that the house was built. Okay? If I look at the next decimal, or the next hexadecimal entry, which is 4 bytes long, we have 08070000. Again, we have big endians, so we have to put that in reverse order per byte. So we're going to put in 00007 and then 08. And you can see our decimal equivalent is 1800, which corresponds to our value in the text file. So you can see the direct correlation to how it appears in memory to what we actually read in, right? The next two values are a little bit more difficult, and it's kind of beyond the scope of this class, but these are doubles, and those are stored in the IEEE 754 floating point number format. And this is kind of a really weird thing to look at when you first review it. It takes a little bit of time to figure it out, but I'll go over it real quickly on the next slide just to kind of demonstrate how you calculate the floating point number. Okay, so for right now, just take it on faith that this 8-bit number right here is going to be equal to this value right here. This next 8-bit value right here is going to be corresponding to this value right here. All right, then we have our 24-bit string. All right, so if we look at that, you can see that it says single, which corresponds to that, but we've got 24 bytes and so on and so forth. So that's going to take up that much space. Now if we look at the next entry, which would be the start of our second struct, you'll see that we have an apartment and its size is 2, or the number of bedrooms is 2, and the number of bathrooms is 2, and you can see the start of that next struct in memory right there, 2 and 2, right? And then we have 2000, and then we have 1800, and so on and so forth. So the whole point of this was to demonstrate how structs will appear in memory, and they're just sequentially placed in memory one after the other based on the data structure. Now another thing that I want to point out is that if we were to run this in debug mode, because that was in release, if we switch to debug mode and run it again, you're going to see a little bit different behavior. Okay, so here you can see, let me pull up the memory location. Okay. Here you can see some extra values that have been entered in. We've got all these CCCs in here, okay? That's part of, again, the debugging part of Visual Studio, inserting certain things into memory to kind of make things easier. Again, outside the scope of this class, but I wanted to make sure that you realize that there's a difference when you're compiling in debug mode versus release mode. Okay, when you debug into release mode, you're not going to have a lot of the extra debug features and symbols that are stored into memory along with the program to help debug it. So all of that was just to demonstrate how structs appear in memory with all of their member variables being compacted one right after the other with no space in between them. And when they're a part of array, they're just structured internally in that memory address one after the other, but the array knows how many bytes the size of the struct is, so when you increment going from one index to the next, it just calculates, okay, well, I know this struct is, say, 64 bytes because of all of its member variables, so it's just going to advance 64 bytes in memory to get to the next part where the next struct would start. Let's take a quick moment to look at how we store a floating point number and how we convert to a floating point number in the IEEE 754 format. Again, this isn't testable, but it's something that you should be familiar with, and I wish somebody would have gone through it, when I was in undergrad. So on most machines, floating point numbers are stored in the IEEE 754 format and require 32 bits of memory. Okay, 1 bit is for the sign, 8 bits is for the exponent, and 23 bits is for the mantissa. And real quick, IEEE stands for Institute of Electrical and Electronics Engineers, if you weren't aware. They're kind of a standards body. Now, it's a version of scientific notation, and if you're a little rusty on that, scientific notation is simply the mantissa times some, 10 to some power, right? That's the exponent, and then we have our mantissa. So this is for the 32-bit version of it. Now, if we're on a 64-bit machine and we have a double precision float, or a double, right, then we're going to have 64 bits available to us. We have 1 bit for the sign, 11 bits for the exponent, and 52 bits for the mantissa, or the significand, as it's also known. So for this example, we're just going to stick to the regular single point float just for simplicity's sake. And if you want more information, there's tons of resources out there. Since we're working with Visual Studio, Microsoft actually has a nice write-up on how to do this, but there's plenty of other resources out there as well. So let's convert this number, 123.0625, to its IEEE 754 standard format. First, we're going to convert both sides of the decimal to binary. Now, I'm glossing over the details on how to do this, but it's easy to look up. You're probably familiar with the non-decimal part and how to convert a decimal number to binary by now. But there's a little bit different process. There's actually kind of like an inverse process for doing the actual decimal side of it. Okay. So once we do that, we then convert to scientific notation by moving the decimal places over to the left. And in this case, we're going to move it 6 places. 1, 2, 3, 4, 5, 6. So that gives us this number right here. Once we do that, we can determine the sign. Okay, well, we're obviously working with a positive number, so we'll go ahead and set our sign bit to 0. If it was 1, it would be negative. Next, we need to get the exponent based on its precision. Okay, since we're converting to a float, we need to bias our exponent with 127. Now, because remember, we can't store negative numbers in memory. We have zeros and ones to work with. So what this does is it gives us a halfway point. Okay, if a number is greater than 127, the compiler it tells it how to shift the bits accordingly, right? So if it's above 127, we're going to have a number greater than 1, and if it's less than 127, then we're going to have a number that's less than 1, or a decimal, right? Or a fraction, excuse me. So for a 32-bit number, we use the precision bias of 127. If we're using a double, we would use 1023 as our bias. And then what we do is we add the number of digits that we moved over, or our exponent, to that bias, and that gives us whatever value that we need to store in our 754. So in this case, since we're doing a float, we have 127 plus 6 because that's how many decimal places we moved over to get into scientific notation. And that gives us 133, which when we convert to binary is equal to this, and then we set that aside. Okay. Now finally, the last bit is we just set the remainder as the mantissa. Note that we don't carry over the leading 1. All right, it's just everything after the decimal, and that gets stored in the mantissa. Now, one thing to note here, and the reason why floating point numbers in the computer don't always have the accurate precision, is because it has to do with dividing things by 2. And some numbers you can't easily divide it by 2, and so you run out of digits as you're trying to get closer and closer to that actual value. You run out of the amount of digits to actually store the correct number. So that's why when we're talking about things in dealing with money and where there's really high precision required, it's not acceptable to use a float or a double. You've got to use special data types that are engineered to store that kind of precision. Okay, but the standard floating point number, there is a little bit of loss depending on the particular fraction that you use. Now this gives us the binary format, and if we want to convert it to hexadecimal, we can do so by breaking the number up into 4-bit groups and then converting each of those groups to their hex equivalent. Now this gives us this hexadecimal number. Now of course, as we've seen on my machine, I store my digits in the big endian format. So if we needed to do that, we just do a byte-wise reversal of the order of the value. And that's all there is to it. That's how you convert this number right here, 1230625, to a hexadecimal equivalent in memory, and using a floating point number. Okay, so let's take a real quick look at this in code, and then we'll move on to the actual lesson. So here's a real quick example. So here I have my main program. I'm declaring a float of 123.0625, like we saw in the slides, and I'm just going to print out the memory location. So let's go ahead and run that, and we can see here that this is where it is stored. So we're going to capture that and put it into our little nifty memory examiner, right? And if we go look at it, we can look at the first 4 bytes of memory, and we can see that in fact 0020F642 was what we had with our slides. So if we switch back to that real quick, you can see right here 0020F642. So anyway, I think that's a fun little walkthrough just to see how things are done under the hood. Gives you a little bit more experience working with the debugger and looking at things in memory. Again, none of this is testable, but I just thought it was worth taking the trip down this path just to show you guys how to do that. We talked about structure design in previous lessons, and I want to conclude this lesson by walking through the process with a mini case study. We're going to apply our structure design process to a sales data analysis application to see how we could use structs for our benefit. And this is a simple application. It's kind of a toy problem, but it really gets to the heart of what we're trying to do here. So this application is for a company with 6 salespeople, and their IDs are stored in a text file, and they're not necessarily in any order. The monthly sales data for each salesperson is also stored in a text file with an unknown number of lines, and it consists of their ID, the month of the sale, or their sales for that month, and then finally the total amount of their sales. So as you can see that here. And again, these aren't in any particular order, and say if a salesperson is on vacation and there's no record for that month, then they just won't have an entry into that file. Your job is to write a program to generate and display sales reports with 2 options. The first sorting by sales ID, and the second sorting by the annual sales amount. This option, or these options, should be presented to the user in a form of a menu like this. So this is what the reports should look like. Here's a sample output of what the sales report by ID should look like. And here's a report of the same thing, but they're sorted by sales amount. So here you can see it's sorted by ID, and then here you can see it's sorted in sales from least to greatest. Finally, the program should keep accepting user inputs until an exit option is chosen. Okay, so you're going to want to keep displaying this menu after you display a particular report. And that's something you're going to find in a lot of applications, right? You want to be able to keep going through different menus. Now, we're not going to go through all of the code to make this application work. That's going to be your job. But what we're going to do is we're going to walk through the thought process of designing the application. So the first step is to identify the requirements. And this has really already been done for you. The program must read and analyze data from two different sources, the sales ID file and the sales data file, and present the user with the menu options to pick a report to generate. And then we need to generate and display those reports. So this gives us a good starting point for our functional decomposition. You can see that we have some clearly defined tasks that we need to perform. These tasks can be further broken down into further subtasks, such as reading in and storing the IDs, and reading in and storing the sales data, then analyzing the data and sorting the data, and so on. How you think about the program or the problem domain will determine your initial steps in designing it. For example, you might create functions to display reports in which they sort the raw data, or you might create different sorting functions and pass the pre-sorted data into one report function. Sometimes some of the design consideration is already done for you, and you need to work within the boundary of the framework as it exists. Remember, programming is usually a team sport, and it's very rare that you're going to get full control over all design decisions. Now, I know when you're taking classes, a lot of times you're working alone, but that's not how you generally program out in the wild. Once you have functionally decomposed your requirements, you can begin to think about the implementation details, like how am I going to structure the program? That is, what algorithms am I going to use, or how is my program going to flow once I start it? It's important to keep in mind you'll have different algorithms for different tasks. What data structures are you going to use, and how will you represent the data in your program? Since this is a lesson on structs, we'll choose to represent the data in a struct like this. You can see here that we're storing this ID as a string, and we're storing the total sales as a double. Note that we're not storing any information about the month where the sales were generated because there was no requirement to do so. For the first part, defining the behavior of our main function, we know we're going to have to do the following. We're going to have to load IDs, we're going to have to load and analyze the data, we're going to have to display the menu, and then give the user the choice to continue. This translates to some rough pseudocode like this. Here we have broken down the problem into subproblems that can be solved individually. By integrating them into the main method, we're also performing the last step of our design process. We can expand on this by writing some stubs to flush out our design at part of our stepwise refinement. So we might get something that looks like this. You can see how our program is starting to come together. At this point, we have a functioning program that we can execute even though it is not complete. And you can see here that booleans have been chosen as the return type to indicate success or failure of the load operations even though they aren't currently used. Why might we want this feature in our load functions? It's something to think about. Also, it should be noted that some of the comments are omitted, and I'm not using function prototypes just for the sake of brevity in screen space. So just don't want you thinking that you can get away with doing this on your homework. So we can now dive deeper and work on our subproblems like loading in the data. Since we have a table with our employee IDs, we need to read that file and add the employee IDs to a data structure. A very basic flowchart would look like this. Note that this doesn't incorporate all the considerations that we need to think about. What if we can't open or read from the file? What if there are more IDs in the list than what we can store in our data structure? So you need to think about your edge cases and your boundary conditions when you're actually implementing this in the code. Similar to our ID file, we need to read in data from the sales file. Again, this is a simplistic view of the flowchart, but the same considerations apply in the implementation details. Like, how do you find the ID in the current list, and how do you add the sales to the record? This flowchart is designed just to give you the thought process of what you need to do, and then you can go in and actually implement each of these functions. And by functions, I mean processes, not actual functions. You may need functions for some of these things. You may just need blocks of code. Another thing we need to think about is how are we going to sort our list of sales? We've covered two options already in previous lessons, selection sort and insertion sort, but there are many other sorting algorithms out there and certainly much more efficient ones. So you need to consider how you're going to tailor the algorithm to fit your particular problem domain. For example, here we aren't working with arrays of integers, but we're working with arrays of sales data. So how are you going to modify the algorithm to support the data structures that you're using? Whether you sort the data inside of the display function or pass a sorted array into the display function will depend on different constraints. But regardless, once the array is sorted, you'll need to display it. This is where you go back to the requirements and make sure that you formatted the output to match what is expected. And you have the tools to do this using the IOStream and IOManipulate libraries, and we've already covered that in previous lessons, so I'm not going to cover it again. But it's your job to make sure that you iterate through the data structure and print the contents out correctly. Remember, designing a program is an iterative, thoughtful process. Seldom will you sit down and write a program from start to finish in sequential order. You'll write some code, test it, and then fix that code and write some more. In fact, there's a whole process of software development called test-driven development. And that's built on this very idea, except for with test-driven development, you actually write the test code first, and then you write the code to make the test code pass. But that's beside the point and outside the scope of this course. The key here is to make incremental changes and compile often to you ensure that you're not getting too far off track. And that brings us to the end of this lesson. Hopefully you learned how C-style structs can be used in a simple program to bundle multiple data items. It can be useful when object-oriented programming is not available in language like C, or for simple cases where object-oriented programming could be overkill. In languages like Python, you'll use the dictionary data structure in a very similar way. This lesson showed you how to manipulate the data in those structures, as well as how to pass a struct into a function by value or by reference. And it also showed you how we can return a struct from a function. Finally, we covered how to create and process an array of structs and their potential use in a simple database application. And of course, we also looked at the IEEE 754 standard as an aside, but again, that's not actually part of the curriculum, just there for your benefit. So that's it for now, and I hope you enjoyed it, and I will see you in the next lesson.